So in my earlier class, I have discussed the solutions of the questions numbering from 31 to 37 in the assignment in Center of Mass and Conservation of Linear Momentum. So next I am going to discuss the solutions of the questions numbering from 38 onwards. Come on, look at the screen here. Next I am going to discuss the solution of the question number 38. Look at the question number 38 on the screen. I will once read it out again. A body of mass m at rest explodes into three masses, two of which of mass m/4 each are thrown in perpendicular directions with velocities 3 meters per second and 4 meters per second respectively. The third piece will be thrown with velocity. Now we consider the body of mass m as one system here. The explosion is caused by the internal forces, and total linear momentum system will not be changed by the internal forces. Therefore, there will not be any change in the linear momentum system as a result of the explosion. So, total momentum system of the three parts into which the body explodes just after explosion can be equal to the total momentum just before explosion. So, let M1, M2, M3 denote the masses of the three pieces into which the body explodes. So, M1 plus M2 plus M3 equal to M. Here it is given that the first two parts have same mass, each equal to m/4. So, we can take M1 equal to m/4 on the left side and M2 equal to m/4. So, we get mass of the third part equal to m/2. The total momentum system of the three parts just after explosion must be equal to momentum system just before explosion, because the explosion is caused by the internal forces, and internal forces cannot change the linear momentum system. So, linear momentum of the system will not be changed as the result of the explosion. So, final momentum system just after explosion will be equal to the initial momentum of system just before explosion. Here Pi bar is the initial momentum system just before explosion. Pf bar is the final momentum system just after explosion. Just before explosion, the body is at rest. So, initial momentum system just before explosion is 0 bar. The final momentum system just after explosion, the vector sum of the linear moment of the three parts into which the body explodes. So, you can write it as P1 bar plus P2 bar plus P3 bar. So, you can write P1 bar plus P2 bar equal to minus P3 bar. That means the momentum of the third piece will be opposite in direction but equal in magnitude to the vector sum, a resultant of moment of the first two parts. It is given that the first two parts move in mutually perpendicular directions. That means P2 bar is perpendicular to P1 bar. If you complete the parallelogram with P1 bar and P2 bar by the adjacent sides, it will be a rectangle. The diagonal of the parallelogram passing through their common point of intersection represent the resultant of P1 bar and P2 bar. The moment of third part will be opposite in direction but equal in magnitude to the vector sum of P1 bar and P2 bar. So if you take modulus both the sides here, you can write modulus of P3 bar. Modulus of vector minus P3 bar will be same as the modulus of P3 bar. That will be equal to magnitude of vector sum of P1 bar and P2 bar. Because P1 bar is perpendicular to P2 bar, magnitude of the vector sum of P1 bar and P2 bar. You can write root of P1 square plus P2 square. P1 is the magnitude of moment of the first part, which you can write M1 V1. V1 is the magnitude of velocity of the first part just after explosion. P2 is the magnitude of the linear of the second part, which you can write M2 V2. V2 is the magnitude of the velocity of the second part just after explosion. Magnitude of moment of third part, you can write M3 V3. V3 is the magnitude of velocity of the third part just after explosion. Can substitute here M1 equal to M by 4 and M2 equal to M by 4, M3 equal to M by 2 on the left side. So you can, on the right side, you can take M1 and M2 are equal, therefore you can take common outside here, each equal to M by 4. So if you simplify this, you get V3 equal to half of root of V1 square plus V2 square. V1 is given to be 3 meter per second. V2 is given to be 4 meter per second. So if you simplify this, you get magnitude of velocity of third part just after explosion will be 2.5 meter per second. So answer is 2.5 meter per second. So the problem is completed. But sometimes you may be asked what angle the direction of the velocity of the third part makes with the direction of the velocity of one of the parts. Let alpha denote the angle made by the resultant of P1 bar and P2 bar with the momentum P vector P1 bar of the first piece. So rectangle opposite sides are equal, so you can take length of this side also equal to mod of P2 bar. So tan alpha you can write mod of P2 bar by mod of P1 bar. That is M2 V2 by M1 V1. Here M2 and M1 are equal. So you get tan alpha equal to V2 by V1. V2 is 4 meter per second, V1 is 3 meter per second. So you get alpha equal to tan inverse 4 by 3. That will be nearly 53 degrees. So the angle between P1 bar and P3 bar will be equal to 180 degrees minus alpha. That is 180 degrees minus 53 degrees. That is 127 degrees. The same way, suppose beta is the angle with the resultant of P1 bar and P2 bar makes with P2 bar. Then alpha plus beta, you can write it as 90 degrees. So you get beta equal to 90 minus alpha. That is 90 minus 37. 90 minus 53 degrees. That will beta comes out with 37 degrees. So the angle between P2 bar and P3 bar, in case you are asked, that will be equal to 180 degrees minus beta, or 180 minus 37. That will be 143 degrees. So for question number 38, second option is answer. See the question number 39. A shell is fired from a cannon with velocity v, an angle theta with the horizontal direction. At the highest point on its path, it explodes into two pieces of equal mass. One of the pieces retraces its path to the cannon. The speed of the other piece immediately after explosion is. So the velocity of the projectile So the velocity of the projectile at the highest point of its path, as I discussed earlier in the theory of projectile motion, will be equal to horizontal component velocity, which will be equal to u cos theta. Where u is the magnitude of initial velocity projection. So here the magnitude of the initial velocity projection is denoted by v. So u is equal to v here. It is given that one of the parts retraces its path and returns to the launching point of projection, launching point or point of projection, which we denote by O. The projectile can retrace the path exactly along the same parabolic path and return to the point of projection if it has velocity of same magnitude equal to u cos theta, but in the opposite direction. That means at the instant just after explosion, let m denote the mass of the projectile before it explodes. So one of the parts with mass equal to m by 2 begins to move in the opposite direction with velocity of same magnitude equal to u cos theta or v cos theta. So let v2 bar denote the velocity of the other part just after explosion. So just before explosion, the vertical component velocity at the highest point, the path of projectile is 0. That means the momentum just before explosion is in the horizontal direction. As the explosion is caused by the internal forces, there will be no change in the momentum as a result of explosion. So one may get doubt, momentum of projectile changes due to the force of gravity. Definitely momentum of the projectile changes due to the axial force of gravity as it moves along the parabolic path. But there will not be any change in the momentum as a result of explosion. So we assume that the time of explosion is very, very, very small. So that for motion under external force of gravity, the instant just after explosion considered to be same as the instant just before explosion. So momentum just after explosion can be equated to the momentum just before explosion. So momentum just after explosion we take, suppose in vector form, m2 v2 bar plus m1 v1 bar. So momentum just before explosion is equal to m into v bar or vi bar just before explosion. So I choose the horizontal direction coinciding with the horizontal velocity just before explosion as a positive direction of x-axis. So momentum just before explosion equal to mass of the body, velocity just before explosion has magnitude equal to v cos theta, but it is direct along x-axis in vector form. We can write as I cap. Mass of each part is m by 2. So velocity of the first part just after explosion you can write just after explosion is v cos theta into minus I cap, because it's the first part return to the point of projection. Means velocity of the first part will be in the opposite to the velocity just before explosion, but has same magnitude equal to u cos theta. So the first part, I show the same figure again. The first part moves along same parabolic path which the projectile has moved before explosion and return to the point of projection. V2 is the velocity. V2 bar is the velocity of the second part just after explosion. So you can multiply the equation with 2 and divide with m. You get V2 bar minus v cos theta into I cap equal to 2v cos theta into I cap. So velocity of the second part, just after explosion, you get 3v cos theta into I cap. So magnitude of velocity of second part just after explosion will be equal to 3v cos theta. In case you are given numerical value of theta, you can substitute that. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 39, first option is the answer. See the question number 40. A toy projectile is made of two parts of equal mass which can be forced apart in flight by a light spring. The projectile is moving forward horizontally at 4 meters per second when the spring pushes it apart. One half goes vertically downwards with initial velocity 6 meters per second relative to the ground. The speed of the other half is. So here I choose the horizontal direction in which the projectile is moving before explosion as positive direction of x-axis. Therefore, the velocity just before explosion for the, we can write it as 4 I cap meter per second. So we can equate final momentum just after explosion to the initial momentum just before the explosion. Final momentum just after explosion is equal to initial momentum just before explosion. The momentum just before explosion is equal to mass of the body into velocity of the body just before explosion. Let VI bar denote the velocity just before explosion. I mean, explosion in the means m is the original mass before it splits into two parts. Final momentum just after it splits into two parts is equal to vector sum of the momentum of the two parts. Both the parts have equal mass. That will equal half of the initial mass. That is, we can add m by 2 into v1 bar plus m by 2 into v2 bar. We can multiply the equation with 2 and divide with m. You get v1 bar plus v2 bar equal to vi bar. Vi bar is the velocity, initial velocity just before explosion. That has magnitude 4 meters per second, but it is in the horizontal direction. So in vector form, the velocity just before explosion, you can write 4I cap meter per second. That means I am choosing the horizontal direction as positive direction of x-axis and vertically upward direction as positive direction of y-axis. So vertically downward direction will be the negative direction of y-axis. It is given that velocity of the first part just after the two parts get separated is very directed downwards. The initial velocity before explosion is directed in the horizontal direction. So V1, and it is given that the first part begins to move downwards with a velocity of magnitude 6 meters per second. In vector form, you can write V1 bar as product of its magnitude and unit vector in the vertically downward direction. That is minus j cap. J cap is unit vector along positive axis, minus j cap is unit vector along negative axis. That means V1 bar can be written as 6 meters per second into minus j cap. So from this you get V2 bar equal to 8 I cap minus 6 j cap meter plus 6 j cap you get meter per second. So magnitude of velocity of the second part will be under root of 8 square plus 6 square meter per second, or that comes out to be 10 meters per second is answer. That will be the answer for the problem. In case we are not asked to find the direction of the velocity V2 bar, you can observe that the velocity V2 of second part has components along positive x-axis and positive axis. That means V2 bar will be directed in this way at some angle alpha above the horizontal. So if you want to, suppose this tan alpha is the angle made by, in case you are asked to find alpha, tan alpha you can write V2y by V2x. That means V2y is the y component of velocity second part and V2x is x component of velocity second part. That will be 6 by 8 or 3 by 4 or alpha equal to 37 degrees. That means velocity second part makes an angle of 37 degrees above the horizontal. But of course, this part of calculation is not needed to answer the question given in the assignment, but this is additional discussion. Here answer is only 10 meters per second. In case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 40, fourth option is answer. See the question number 41. A gun fires a bullet of mass 50 gram with a velocity of 30 meters per second. Because of this, the gun is pushed back with a velocity of 1 meter per second. The mass of the gun is, here we consider the gun and the bullet together as one system. So here the momentum system is not changed as a result of firing of the bullet. So when the bullet is fired from the gun, the gun exerts a force on the bullet in the direction of the firing. From Newton's third law, to every action there is always equal and opposite reaction. So if action is the force on bullet by the gun, reaction will be the force on the gun by the bullet. So the gun recoils backwards due to this reaction force exerted by the leaving bullet on the gun. So momentum of the system is not changed by internal forces between the objects in the system. Therefore, momentum of the system of the bullet and the gun is not changed as a result of firing of the bullet in the horizontal direction. So initial momentum in the horizontal direction just before firing the bullet is 0. Final momentum of the system of the gun and the bullet just after firing is the vector sum of moment of the bullet and moment of the gun. So the instant just after firing, moment of recoil of the gun is opposite in direction but equal in magnitude of moment of the bullet. So moment of recoil of the gun is equal to mass of the gun into velocity of recoil of the gun. Momentum of the bullet can be written as mass of the bullet into velocity of the bullet. VB bar is the velocity of the bullet just after firing. Small m is the mass of the bullet. Capital M is the mass of the gun. VG bar is the velocity of recoil of gun just after firing. The negative sign indicates that the velocity of recoil is opposite to the velocity of recoil of gun is opposite to velocity of bullet. So if you consider only magnitudes, mass of the gun into magnitude of velocity of recoil of gun is equal to mass of the bullet into magnitude of velocity of bullet. Here mass of the bullet is given as 30 grams. So small m is 30 grams means 30 to 10 power minus 3 kg. Magnitude of velocity of bullet just after firing is given to be 30 meters per second. Mass of bullet is 50 grams, or not 30 grams. Correct it is 50 grams. Mass of the gun we denote by capital M. Magnitude of velocity of recoil of the gun is given as 1 meter per second. So this you can simplify this. You get mass of the gun as 1.5 kg. So for question number 41, which I have just now discussed, the third option is answer. See the question number 42. Look at the question number 42. Find the coordinates of center of mass of the L-shaped frame of wire. So it is understood or assumed that the wire is uniform. That means it has same mass per unit length or same mass linear density throughout, or same thickness and same density. So the center, let M1 denote the mass of the first part of the wire, which is lying on x-axis with length L by 4. Let M2 denote the mass of the other part of the wire, which has length 3L by 4 along y-axis. Come on, look at the solution. In case you want to copy the diagram, you can copy the diagram on your paper or notebook so that you can understand the solution which I am going to discuss. Now here, so let M1 be the mass of the part of the length lying on x-axis, that you can write mass per unit length into length. Let nu denote the mass per unit length, otherwise the mass of unit length of the wire, which we call mass linear density. Mass M2 of the other part lying on y-axis is equal to length of the part lying on y-axis into nu. The C1 is center of mass of M1, which lies at geometric center of M1. That is a geometric center of length L by 4. So half of L by 4 will be L by 8. So x coordinate center of mass C1 of the first part of the wire is L by 8 and y coordinate is 0. For second part of the wire, which has length 3L by 4, the center of mass is at C2. That means C2 is the center of mass of part of the wire with length 3L by 4, which will be at half of its length. That is half of 3L by 4 will be 3L by 8. So x coordinate of center of mass of second part is 0. Y coordinate is 3L by 8 because it lies on y axis. So here y coordinate is 0 for first part. X coordinate is 0 for second part, y coordinate is y2. For first part, x coordinate x1, y coordinate is 0. Now x coordinate center of mass of the two masses M1 and M2 can write M1 x1 plus M2 x2 by M1 plus M2. Can substitute the values now. M1 equal to L by 4 into nu into x1 is L by 8. M2 equal to 3L by 4 into nu. X2 is 0. By M1 plus M2, L by 4 into nu plus 3L by 4 into nu. So you can take L by 4 common, otherwise you can second term numerator is 0. The denominator you get L into nu. So L into nu gets cancelled here, both numerator and denominator. So you get L by 32 is x coordinate center of mass. Same way you can find the y coordinate center of mass also. Y coordinate center of mass is given by M1 y1 plus M2 y2 by M1 plus M2. Come on, copy down. In case you want to copy the solution of this problem, you can take a pause and copy the solution of the problem and complete the calculation of y coordinate also yourself. M1 plus M2 is L into nu. So get y coordinate of center of mass 9 by 32 into L. If you want to copy the solution, you can take a pause and copy the solution of this problem. See the question number 43. A man weighing 80 kg standing on a trolley weighing 320 kg. The trolley is resting on frictionless horizontal rails. The man starts walking on the trolley at a speed of rails. That means the trolley is on the rails at a speed of 1 meter per second. Then after 4 seconds, his displacement relative to the ground will be. That means the 1 meter per second, actually the velocity of the man relative to the trolley. I have actually discussed similar question with a small difference. So we consider the man and the trolley together as one system. The man and trolley together as one system we consider here. So momentum system remains conserved in the horizontal direction. Let M1 denote the mass of the man, which is given to be 80 kg. Let M2 denote the mass of the trolley, which is given to be 320 kg. The magnitude relative velocity of the man with respect to the trolley. Mathematical denote by V bar subscript 1 2. Let us denote it by V bar simply, otherwise. That is equal to 1 meter per second in magnitude. So our mod of V bar you can write 1 meter per second. So here we consider the man and the trolley together as one system. The total weight of the system of the man and trolley is balanced by the normal reaction forces by the rails on the trolley. So there is no external force on system in the horizontal direction. So total motor system of the man and trolley remains conserved. So final momentum system of the trolley and the man just after the man begins to walk must be same as the initial motor system. Initial motor system is 0 because both the man and trolley are initially at rest. So final motor system we can write M1 V1 bar plus M2 V2 bar. Or you can write M2 V2 bar equal to minus of M1 V1 bar. Now relative velocity of the man with respect to the trolley, which I have denoted by V bar, you can write as V1 bar minus V2 bar. You are asked to find displacement of the man relative to the ground after 4 seconds. For that, you must know the velocity of the man with respect to the ground. Here, V1 bar is the actual velocity which a man walks on the trolley relative to the station observed on the ground. And V2 bar is the actual velocity of the trolley with respect to station observed on the ground. V bar is the relative velocity of the man with respect to the trolley, which has a magnitude of 1 meter per second. So from this, you can write V2 bar, you can write in terms of V1 bar. You can substitute the value of V2 bar from first equation into second equation. You can write V2 bar from first equation equal to V1 bar minus V bar. Equal to minus M1 V1 bar. You can solve for V1 bar here. You can carry the terms containing V1 bar to the left side of the equation. Don't put bar symbol for mass. Mass is scalar. So solve for V1 bar here. You get M1 plus M2 into V1 bar equal to M2 into V bar if you simplify this equation yourself. So V1 bar equal to M2 by M1 plus M2 into V bar. Here M2 is 20 kg, M1 is 80 kg. So V1 bar you get 320 by 400 into V bar. So 0.8 into V bar. So that means V1 bar is in the direction of V bar. So mod of V1 bar, that is magnitude of velocity of the man related to the ground, is 0.8 times the magnitude of V bar, that is 1 meter per second. Or 0.8 meter per second is the magnitude of velocity which the man walks with respect to station observed on the ground. So magnitude of the displacement of the man are denoted by S1. In a given time interval, assuming the velocity to be uniform, magnitude of velocity of the man with respect to the ground into time interval. Magnitude of velocity of the man with respect to the ground is 0.8 meter per second. And the time interval for which displacement is required is 4 seconds. So magnitude of the displacement of the man relative to the observer on the ground is 3.2 meters. So answer is 3.2 meters. In case you want to copy the solution of this problem, you can take a pause and copy the solution of the problem. So for question number 43, which I have just now discussed, the second option is the answer. See the question number 44. Which was originally given one of the world IIT papers as mentioned within brackets. The same question as it is also given one of the previous EAMCET exam papers. Particle of mass 4m which is at rest exposed into 3 fragments. 2 of the fragments each of mass m are found to move with speed v in mutually perpendicular directions. The total energy released in the process is. This problem is similar to the question number 38 I have discussed earlier. Only difference is we are asked to find the total energy released in the process. That means you have to first find the speed of the third part by following same method like in the question number 38. So similar to the question number 38, here also explosion, we can assume that explosion is caused by internal forces, and internal forces cannot change the total amount of system. So if Pi bar is initial momentum just before explosion, Pf bar is the final amount of system just after explosion. You can write Pf bar equal to Pi bar. Initially, the mass is at rest, mass system of which mass 4m is at rest, so initial amount of system is 0. The final amount of system just after explosion is the vector sum of the momenta of the 3 parts. So P1 bar, P2 bar, P3 bar denote the momentum vectors of the 3 parts into which the body explodes. So at the instant just after explosion, the momentum vector of the third part will be opposite in direction but equal in magnitude of resultant momentum of the first 2 parts. The first 2 parts are moving in mutually perpendicular directions. So P2 bar is perpendicular to P1 bar. And first 2 parts have same mass and same magnitude of velocity. So mod of P2 bar is same as mod of P1 bar. So you can complete a rectangle with P1 bar and P2 bar by the adjacent sides. The diagonal represents the resultant of P1 bar and P2 bar. Because P1 bar and P2 bar have same magnitude, the resultant bisects this angle between P1 bar and P2 bar. So resultant of P1 bar and P2 bar makes an angle of 45 degrees with P1 bar and 45 degrees with P2 bar. The momentum vector third part will be opposite in direction to the resultant of the P1 bar and P2 bar, as shown in the figure. So if we take modulus both sides, modulus of P1 bar plus P2 bar is equal to modulus of minus P3 bar. Modulus of minus P3 bar is same as modulus of P3 bar. Because P1 bar is perpendicular to P2 bar, we can write mod of P1 bar plus P2 bar is equal to root of P1 square plus P2 square. The sum of the masses of the 3 parts is given to be 4m. The original IIT paper, same question given also in one of the previous EAMCET papers. You are given the ratio of the masses of the three parts like this 1:1:2. So that means we get M2 is same as M1 and equal to M. M3 is 2M. The first two parts which have same mass move in mutually perpendicular direction, same magnitude of momentum. That means P2 equal to P1, each equal to M into V. Magnitude of moment of third part is equal to on the right side. Magnitude of moment of third part, mod of P3 bar, you can write mass of the third part into magnitude of velocity of third part. This left side you can write root of 2m square v square. Mass of third part equal to m. So that is mv into root 2 by 2m. So magnitude of velocity of third part just after explosion will be v by root 2. Total energy released is equal to total kinetic energy of the three parts into which the body explodes. That is sum of the kinetic energies of the three parts. The first two parts move with velocity of same magnitude v. So mass of the first part is m, magnitude of velocity is v. Mass of the second part is also m, magnitude of velocity is v. Mass of third part is 2m and magnitude of velocity is v by root 2. If you want to copy down the solution of the problem, you can take a pause and copy down the solution of this problem. You can simplify this yourself. Finally, you get the answer as 3 by 2 mv square. So for question number 44, third option is answer. Look at the question number 45. Look at the question number 45. Four particles of mass of m, 2m, 3m, and 4m are at the vertex of parallelogram and xy plane with one of adjacent angle 60 degrees and smaller side A and larger side 2A. The mass m is at the origin, mass 4m on x-axis. The center of mass system is, if you want to copy the diagram, first you copy the diagram yourself, copy the data so that you can follow the solution which I am going to discuss now. You can take a pause and copy the solution. The first particle of mass m is at the origin of the coordinate system. The x-axis is along the side of length A. The length of the other side is 2A. So let us call this corner as A, this is B, C is the third corner of the parallelogram, which has where mass 3m is placed. Let D be the fourth corner of the parallelogram at which the mass 4m is placed. So the first particle is at the origin. Therefore, x coordinate is 0 for the first particle, y coordinate is 0. Mass m1 you can write m. Second particle lies on x-axis with mass m2 equal to 4m. X coordinate for second particle you can take it as a. Y coordinate is 0 because it lies on x-axis. For third particle, now this angle is 60 degrees here. Let x3 y3 denote the Cartesian coordinates of third particle. Drop a perpendicular from the vertex C on x-axis. So this is the x coordinate for the third particle. This length, this angle is 60 degrees, so this angle is also 60 degrees. Length of side BC is 2A. So this length you have to find. Let n be the foot of the perpendicular dropped from C on x-axis. So in the triangle BCN, cos 60 degrees is equal to BN by BC. Cos 60 degree 1 by 2. BC is equal to A. So you get BN equal to A. Therefore, x coordinate for the mass M3 of third particle is 3m. The x coordinate for third particle distance from A to N, that is A to B plus B to N, that is A plus A, that is 2A. Let y, this is x3. Y3 is the y coordinate for third particle, equal to height of the triangle CN. Again, in the same triangle BCN, sine 60 degrees, you can write CN by BC. So you get sine 60 degrees root 3 by 2. CN equal to Y3. BC equal to A. So y coordinate for third particle is equal to A root 3. For fourth particle, the x coordinate is x4. Y coordinate is y4. By similar procedure, you can drop a perpendicular from the point D on x-axis. This is the x coordinate for fourth particle. So you get x4 by A cos 60 degrees in this right angle triangle. This length is 2A. So cos 60 degrees is equal to x4 by 2A, or x4 equal to 2A cos 60 degrees. Cos 60 degree 1 by 2, so you get x4 equal to A. Y coordinate for fourth particle is same as the y coordinate for third particle, that can be taken as A root 3. Now use the equations for coordinates of center of mass. The x coordinate of center of mass is given by m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 by m1 plus m2 plus m3 plus m4. You take a pause and complete the calculation yourself. Substitute the values of x, all m1, m2, m3, m4, and x1, x2, x3, x4. Similarly, y coordinate center of mass equal to m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 divided by m1 plus m2 plus m3 plus m4. You copy the calculation part, take a pause and copy the calculation, complete the solution of the problem.